let's look at this sample test for Physics 214, Fall 23. So first problem, let's convert the following to the units indicated. So when you're doing this, make sure you show all your unit conversions. So we've got 50.1 times 10 to the negative 5 kilograms. We want to go to milligrams, so we'll do a couple of fractions here. So 1 kilogram is how many grams? 1,000 grams. So that'll be your first fraction. And then we want to get to milligrams, and so we've got to cancel out so that'll cancel the kilograms. So we want to get to cancel the grams too. So we can do 1 gram is 1,000 milligrams. All right, so if we multiply that out, we can see that we're going to end up with grams. We can write a little more detail, I guess. 50.1 times 10 to the negative 5 times 1,000 times 1,000 and divided by 1, and then that will end up being milligrams. Looking at this, this is 10 to the third, this is 10 to the third, so adding the exponents, we got 10 to the sixth, then 10 to the negative 5, so it's all together just 10 to the 1. 50.1 times 10, or 501 milligrams. So looking at our significant digits, we started out with 3, so we can keep 3, so that's good. So we can say 501 milligrams, or we could say 550.1 times 10 to the 1, that would be fine also. All right, for the next one, we got meters per second. We want to go to kilometers per hour. So let's say 11.1 meters per second. Let's get the meters converted first. So we need meters on the bottom, we need kilometers on the top. So 1 kilometer is 1,000 meters. The meters will cancel. And we got to get seconds to hours. So we can do 60 seconds, 1 minute. And then, so that gets rid of the seconds, but now we're in minutes. We want hours, so we can do 60 minutes is 1 hour. So just all of our fractions are things that are equal to each other, so we're not changing the total number here. And so if we want to put it all together, minutes will cancel. And so we will have 11.1 times 60. It's 11.1 times 60 times 60 divided by 1,000. And the units that are left after all the canceling, all we have left is kilometers on the top and hours on the bottom. So kilometers per hour. Plugging that into our calculator, 11.1 times 60 divided by 1,000. And we end up with 39.96. But we only have 3 significant digits, so we got to round this to 3, and that's kilometers per hour. We got to round this to 3, so that would be 40.0 kilometers per hour. So 40.0 up here. All right, to 3 sig digs. So when we're multiplying things out, look at the significant digits of the least number in the multipliers, and since all these are exact conversions, they have full significant digits, they won't cancel, they won't cut down the number for that. All right, number 2. We're supposed to do the multiplication here and get the correct number of significant digits and the units. All right, and so we just put in our calculator 3,000 times 0.000123. We end up with 0.3702. All right. Looking at significant digits, though, this one only has one significant digit. All right, so our answer can only have 1 significant digit, so that means we have 0.4. Units, we'll just keep it in grams. All right. For part B, we've got centimeters and millimeters, so we can make a choice. Do we want to add, or do we want to convert the millimeters to centimeters or the centimeters to millimeters? Let's go to centimeters, I guess. So let's change 505 millimeters. We want to convert from centimeters to millimeters. So we'll say 1 centimeter is 10 millimeters. That's as good as any conversion, I guess. And so we're going to divide by that, so we will end up with 50.5 centimeters for the 505 millimeters, and then we're going to add to that the 99.9 centimeters. So we get 150.4 centimeters, and since both of them had a tenth place is significant, so we just keep that 150.4 centimeters. All right, and so even though we only have 3 significant digits in each of these elements of the question, we can have 4 in the answer, because when you're adding or subtracting, you just look at the how many places after the decimal point are in all of your numbers, and since both of them have 1, we can keep 1. Okay, looking at number 3, we have vectors here. My printer didn't work real well, but so we've got A going straight up and down, only in the y direction. We've got B that's at an angle of 30 degrees. And we've got C that's coming down at an angle of 45 degrees from the horizontal. All right. And so it says A and B are 4 meters long, and C is 6 meters long. And we want to know what is C sub x and C sub y. So here's C. We said that it says the length is 6. All right, angle is 45, so you want the pieces. So this part here is, we got x horizontal, y vertical. So this would be what we call C sub x, and this is what we call C sub y. And just looking at the triangles, x is next, and then of course the C, the 6, is the hypotenuse. C sub x is next to the angles, cozy to the angles, cosine. So if we want to go all the way back to the definition of cosine, we would say cosine 45 degrees equals C sub x over C. Rearranging that to solve for C sub x, we get C sub x equals C cosine 45 degrees. And so we can plug in and get C sub x then is 6 cosine 45 degrees. We can put in our calculator, or we could just do 6 square root of 2 over 2, but 6 times, we'll just plug it into the calculator, cosine of 45. And let's just get a decimal number. 4.243 for now. Similarly, looking at the other side, C sub y is related to sine. We can say, go back to the definition if we have to. Sine 45 equals cy over c. So cy is c sine 45. So cy is 6 sine 45. And just knowing sine and cosine of 45 are the same, so it's a isosceles triangle here. Cy is also going to be 4.243 meters. Looking at the answer though, we only have, or at the question, we only have 2 significant figures there, so kind of running out of room here, but we'll say C sub x, or let's just do C in bracket kind of form. C is going to be equal to 4.2 comma 4.2 meters. So there's our answer for part A. All right. For part B, it says, what is A plus C? All right, so when we add vectors, we have to add x's to x's, x parts to x parts, and y parts to y parts. So let's look at A. X part is 0, right? There's no sideways component to A. So AX is 0. AY, I said it was 4 long, so AY is 4. All right, so if we're going to call it D, so DX is going to be AX plus CX, which is just going to be 0 plus 4.2, so 4.2. And then DY is AY plus CY, which is, whoops, I just screwed up. Or I just realized I screwed up. All right, so C, both of these are negative, right? Because it's going backwards and down, so these should both be negative. And so looking at doing it with the triangles, you got to look at the directions that it's going in terms of x and y. So don't forget that. So I need minus 4.2, minus 4.2 there. Now this one, A is going up positive, so it's going to be 4 plus negative 4.2. So it's going to be 4 minus 4.2, so negative 0.2. All right, so D as a set of points, X negative 4.2, Y negative 0.2. All right, so this would be my solution for D. Okay. A squeaky chair, sorry about that. All right. So we have a rocket sled. So we have a kinematic equation. Things are moving, right? We're talking about acceleration, position. It says we can assume constant acceleration and no friction. All right, so part A. What is the rocket's average acceleration? So you should hopefully have on your equation sheet A average acceleration is delta V over delta T. Delta V, remember, is V2 minus V1, or final minus initial, over T2 minus T1, just the change in velocity over the change in time. It's going to be 60 meters per second minus 0 over 5 seconds minus 0. So 60 over 5. So A average is 60 over 5, which is 12 meters per second squared. Just checking significant digits, it looks like we have 2, so 12 is good. All right. Starting from rest, how long does it take a rocket sled to cross the field? So starting from rest is giving you a clue that it's not moving at the start, no speed at the start, so V naught is 0. How long does it take it to cross the field? So going all the way across the field is kind of telling us that it's telling us what happens in X. So let's use our X equation. So we should have an X equation. X equals X naught plus V naught T plus 1/2 AT squared. All right, so we'll kind of assume we're starting at X equals 0 and going across the field. So the total X will be 200. So X naught is 0. X maximum, or X at the condition we're looking at, is 200 meters. V naught T, we just said that V naught was 0, so that one's going to go to 0. And we have 1/2 AT squared. It says constant acceleration, so we got the acceleration here, so we know that A is going to be 12. All right, so we know everything except for T in this equation, so let's use that to find T. So these two terms are 0, so let's just rewrite it. 200 equals 1/2 of 12 T squared. All right, so this becomes 6, divide through by the 6, so we get 200 over 6 equals T squared. So T is the square root of 200 over 6. So square root 200 divided by 6. We get 5.774 seconds, but again, we only have 2 sig digs, so T equals 5.8 seconds for part B. Alrighty, part C. How fast is it going when it reaches the end of the field? Alright, so how fast? This is a velocity. Alright, so what is V? When it reaches the end of the field, we can use another one of our kinematic equations. V equals V naught plus AT. Right, and again, we already said V naught was equal to 0. We know A is equal to 12. We just calculated T. 5.8 with the rounding, but let's go back to keep a few more sig digs in the process. So let's say 5.774 seconds. And so V naught is just equal to 12 times 5.774. Oops. 69.29 meters per second. But again, 2 sig digs, so V is equal to 69 meters per second. All right, so again, you just using our basic kinematic equations, some of the definitions of acceleration kind of things, solving for what we can find. Okay, let's look at the number 5. Draw a free body diagram for each of the masses, include forces, acceleration, direction, coordinate axes, x and y components of force vectors. All right, so we've got 2 masses, so we're going to have, let's see, M2, M1 are a certain size. Draw the free body diagram for just M2. All right, so we're just doing one of them. So M2 is here. Always have gravity, so we're just going to do F of gravity equals M2G. All right, and we have opposing gravity. We have the force of this string pulling up. We'll just call it T. All right, so that's all we have for forces on this one. Glue the forces, good. Acceleration, direction, so we don't really know. Oh, let's see, we have M2 is smaller than M1, so we would expect M1 to go down, so let's just say acceleration direction is up. All right, if we didn't know it, we could just take a guess, but we'll just go with that. And then our coordinate axes, let's just do x and y as we normally would. And the components of the force vectors, since they're all straight up and down, all forces are just in the y direction, so we don't need any components for that one. Okay, for B, for M3, so M3 is here. It's a little hard to read. M3 is the one on the slope. It has US and UK, so that means we're talking about friction. M3 is 10 kilograms. M4 is 5 kilograms. Draw the free body diagram for M3. So we're wanting the one on the slope. Okay. Again, let's just do gravity first. F for gravity is mg. We'll have to do some components for this one though. And we have the tension of the string pulling up the slope. This is T. Call it T. And let's see. M4 is 5, M3 is 10, so we would probably expect it to go down this way. So let's just call that our positive A direction. And then let's also just do X and Y with the slope. So X is going up the slope, Y is going straight up perpendicular to the slope. All right, we might be missing a few things here though. So that's probably okay to have my coordinate axes there. Hopefully it's not in the way. So whenever we have something on a slope, something's got to be holding it up from falling through the floor, right? So we got our normal force. It has to be perpendicular at right angles to this surface. Let's see if I can get the kind of a normal force there, and perpendicular. And then we are including friction, so this friction would be going against the force pulling in the other direction, although it's actually going against the motion. Let's see. Which way do I want to draw my force of friction? If we are assuming that it's moving, yeah, so I probably did my, I should probably turn it around. All right, so let's do the force of friction also. Going uphill, since we're saying acceleration is downhill. We have to say our force of friction is going uphill. Right, because friction always slows you down. Whichever way you're going, it's going to fight against you. So if we're saying that the block is going down, then friction has to be pointing up in the same way as tension, as the string. Okay, maybe a little bit of a weird problem. All right, so now we need to break up. So we got our forces listed. We got our coordinate axes, we got our acceleration direction, but we need the components of the forces, X and Y components, because T is only in X, N is only in Y, but and F friction is also, I'm sorry, T is only in X, F friction is only in X, and N is only in Y, but our gravity has two components. All right, so we can draw our triangle here, trying to draw one part perpendicular to the surface level and then one part parallel to the surface level. So it comes down and then it goes this way. So this little piece in here is F sub G in the X direction. This piece over here is F sub G in the Y direction. All right, we got the angle in here is going to be the same as the angle here. All right, because of the, if we had the, how to draw it, but if we had the surface flat here, we have a 30 degree, yes, 30 degree angle let's see if we could continue this here. This angle plus the 30 degree angle I think it needs a little bit bigger. We did this in class, but let's just look at it one more time. All right, so here's our mg, here's our f sub gy, and here's our f sub gx. We're trying to prove that this angle is 30. All right, so if we have this as 90, this is straight up and down, supposed to be. All right, so this angle would be our 30, and so 30 plus whatever this would be, alpha, is 90 degrees, right? And so inside the triangle, alpha plus whatever this is has to be 90 degrees, so that means this also has to be the 30 degrees. All right, generally the slope angle will be the angle between mg and fgy. Okay, and so then getting the components fgx, x is opposite the angle, so it's going to be mg sine 30, and fgy, y is next to the angle, cozy to the angle, so it's going to be mg cosine 30. Alrighty. And we could put in the numbers and get actual numbers if you wanted to, or we can leave it in equation form. Is fine with me, as long as I can see how you're breaking down the components. All right, I think that's all the parts of that one. 5 continued. A mass of 50 kilograms riding in an elevator, accelerating upward at 2 meters per second. Okay, so we're going to have some sort of mass sitting in an elevator. Okay, in terms of the free body diagram, it's going to have, again, it's got its weight. It's got some sort of, it's sitting on the floor of the elevator, we'll assume, so it's got some sort of normal force pushing it up and accelerating upwards. So we got A positive up, and we got X and Y. All right, and so there's not much more to it than that. There's no sideways stuff mentioned, so this would probably be it. No breaking it up into X and Y components. It's all Y components. Just for fun, let's write Newton's second law. So F net in the Y direction is going to be N minus mg. Right, and that's going to be equal to MA. And so if you look at it, solve it for N, we would have mg plus MA, or mg plus A, whatever. And so when you're going up in the elevator, the normal force, what's pushing you up, which is kind of like how heavy you feel, is going to be more than gravity, right? The acceleration of the elevator plus gravity, so you feel heavier when the elevator is going up. If A was negative, is going down, then you'd be subtracting from gravity and you'd feel lighter. Okay, just a little side note there. The main part of the problem was just drawing the free body diagram. All right, let's look at number 6. So we've got a mass and a person pushing up. Let's just call it P, a push, something like that. Up on it, we've got 25 degrees in here. Couldn't see it. Okay, we got coefficients of friction, US and UK. So we're going to be thinking about friction. We've got a mass given. And so it says draw the free body diagram, include coordinate axis and direction. For acceleration, it'd be good to maybe break it into components while we're here too. All right, so here's our mass, boysies. All right, so we've got mg, F of gravity, mg going down. We've got our normal force perpendicular to the surface. We've got friction, since it's moved, we've got, well, let's go ahead and put the push up here, so we'll assume it's going up, so then friction is going to push against that, so we'll call this F's of friction. Alrighty, that looks like pretty much all we need. We need our coordinate axes though. We got, let's just go x lined up with the slope, then y perpendicular, or lined up with the normal force, and we'll assume acceleration is up the hill. Hopefully the person's pushing hard enough to go up the hill. And FG needs some components, and so let's try to make this look like it's supposed to. We're going to need one that's perpendicular to the surface and one parallel to the surface. Parallel to the surface will be FG in the x direction, and then FG in the y direction is coming down. Again, the same argument we had before. When you have a slope like this, the angle becomes the angle inside here. It's 25 degrees. And so we can say FGX is mg, x is opposite the angle, sine 25. In this case, we know m, so let's just say that's equal to 45 times g, 9.81, and sine 25. Everything, we got kilograms, we've got g is in meters per second, so we know this is going to come out to be newtons. Let's just do it in a minute. 45 times 9.81 times, sine of 25. So we get 186.6 newtons. And then let's do FGY. mg, but now y is the one cozy to the angle, cosine 25. So again, 45, 9.81, cosine 25. So FGY is 400.1 newtons. All right, so it's not necessarily required as for drawing the free body diagrams to give the actual numbers, but I have a feeling it's going to be helpful down here in a minute. So I went ahead and calculated it. Part B, write Newton's second law equations in both directions. So we'll do F net in the x direction equals m a in the x direction. All right, so doing that, let's look at the x direction here. We've got negative p, because it's going against x, plus F of friction, because it's going in the same direction. Gravity is going, the gravity component in the x direction is going in the same direction as positive x, and so plus FGX equals, all right, so that's F net, all the forces in the x kind of direction, equals mass m times acceleration in the x direction. All right. We can simplify this a little bit, or do a little bit more calculations. Let's go ahead and write, where should we write this? well, let's just leave it in general for now. F net in the y direction is going to be ma in the y direction. And so looking in the y direction, we have normal force is positive, and then we have negative part of gravity, Fgy, and that's going to be equal to mass times acceleration in the y direction. All right, so for most of these problems, when we have the y direction is just when we have mass just sitting on a slope, not going up or down, according to the normal, the a sub y is going to be 0. And that's the same as in this case. And so that whole thing is going to be equal to 0. But in terms of just writing the equations, these are the equations. And that's what it asks for in part B. Part C, it says find the force needed to get the mass to start moving. All right, so for this one, we're going to need to put in some more details about the force of friction and so forth. And so let's go ahead and calculate it. So to start moving means it's not moving. All right, so we're going to use F of friction is going to be mu sub s, static friction, times the normal force. We can use this equation to solve for the normal force. So we've got n minus Fgy equals 0. So we can say that n is equal to Fgy, and Fgy, we already calculated, was 400.1 newtons. All right. So the force of friction then, mu sub s, 0.25, and then n is a 400.1. So F of friction for this part, okay, for part C, is 0.25 times 400.1, 100.0 newtons. All right. And we have Fgx from over somewhere here. And so we can put some stuff in here. Find the force needed to get for the mass to start moving. Oh, to just start moving. So it means it's not moving at the moment, right? It's just about to start. We're just at that edge of maximum friction, just overcoming that maximum static friction. And so in this case then, just to start moving, we had excuse me, we have that a sub x is also equal to 0 because it's not moving yet. It's just about to start, just on that tipping point. So we can use this equation up here, the x direction equation, with a sub x equal to 0 for this case. And so let's rewrite that down here. We've got negative p plus, so this equation coming down, F sub friction, we just calculated 100.0 newtons, and then plus F sub gx, 186.6 newtons, equals m a sub x, but we just said a sub x is equal to 0, so it's m times 0, which is 0. All right, so we can just solve this for p. So bring p to the other side. P must be 100 plus 186.6. So P is 286.6 newtons, but we wanted, how many sig figs do we have? We only have 2, so P is 290 newtons. Alrighty. Then it says, let me just check my numbers here, see if I got the same numbers before. Looks good. I didn't round, but that's 290 newtons. Okay. All right. So for the next part then, it says keeps pushing with the same force, but now it's moving, right? So now that it's moving, we have a new force of friction because we got to use kinetic friction, mu sub k times n. And a sub x will not be equal to 0, right? Because it's moving. We will still have a sub y equals 0 because we're assuming it's not flying up off of the ground, off of the incline, and so that one still works. All right, so looking in the y direction, like I said, this acceleration is still 0. Everything is still the same, so we can still use Fgy is 400. We will have a new F of friction though, so let's go ahead and calculate that. F of friction is equal to mu k times n, so mu k is 0.1. Remember, kinetic friction is usually less than static friction. And then N is still the same, 400.1. All right, so it looks like about 40. 0.1 times 400.1, 40.01 newtons. Alrighty. The force of gravity, FGX, is still going to be the same. Nothing has changed how much gravity is acting on this guy. So we use this equation again, but now bring it down here. And so, oh, it says keeps pushing with the same force, so we can still use this P also. And so I guess let's just rewrite it. So negative P plus force of friction plus FGX equals now M, we'll just say MA, or we can call it MA sub X, that's fine. So we know P, we know F of friction, we know F of gravity, we know M, and so we can solve for AX. So let's just put it all in and solve it then. So we got negative 290 plus the force of friction, 40.01, plus the X component of gravity, 186.6. These are all newtons, so we're in good shape, equals M times A. M is 45 times AX. Add those all together. Negative 290 plus 40 plus 186.6. So we get hold on. I said acceleration was up against x, so this should be a negative max. It was 0 before for this part, so it didn't really matter. So I need a negative on my max here because acceleration is going in the negative x direction. So I should have a negative max here, so I should have a negative here, which is good because I end up with a negative 63.4 equals negative 45 ax. And so then ax is 63.4 over 45. .41 meters per second squared. Oh, what did I do? Oh, let's go ahead and keep a few more sig digs when we're doing this. 286.6 negative. See if that works out a little bit better. Negative 60.0. Sorry. Oh, okay. So, I don't know. I wasn't looking at the screen to see how much you could see. So, anyway, force of friction with the mu k is here. Went ahead and calculated that to get the 40.0. Rewrote this P equation. Decided to keep more sig figs here. And then the negative sign problem. Got negative on the AX. Alright, so you get negative 60 here. And so then if I get 60 divided by 45, 1.333 meters per second squared, which agrees more with what I had before. 2 sig figs, 1.3 meters per second squared. That's A or AX. There. Alright, sorry it was off the screen there. Hopefully you can catch up with that. So generally when you're doing more calculations, go ahead and use ones with a little more sig figs just so that you don't get rounding errors creeping in. So when I used the 290, I had a fairly big error compared to what I had used when I didn't do the rounding before I started solving. Okay. Alrighty, we got a gymnast climbing a rope. Given the acceleration, draw a free body diagram, include acceleration. So we're going to have this person climbing a rope. Anyway, this is a person. Terrible person. Let me just draw a person. Just draw a person. Alright, pretend like they're climbing a rope. Alright, so the gymnast has a mass. So we got force of gravity, mg. Force of gravity is mg going down, and we've got some sort of rope. She's pulling on the rope, but the rope is pulling back on her, giving a tension. Her or him, I don't know, going straight up. All right. So this would be, we could calculate that value. I don't know if we need it. We might. mg, so we've got m is 50 kilograms, and g is 9.81 meters per second squared. So force of gravity for 90.5 newtons for this gymnast, and that's straight down. The tension, we don't know that. Include the gymnast acceleration. So it says she's going up, so we'll do a plus that way, and we'll just do x and y the normal kind of way. Alright, write Newton's second law equations for the gymnast in both directions. Well, so F net in the x direction, we got 0 force in the x direction is equal to m a in the x direction, which is also going to be 0, so 0 equals 0. It's a pretty boring equation there. But F net in the y direction, we got t is in the positive y direction, we got minus F of gravity in the negative x direction, or negative y direction. We can put in numbers. We can say that's going to be t minus 490.5 if we want to, and that's going to be equal to mass times acceleration in the y direction. And we were given that she's going up the rope, or climbs the rope, with acceleration of 0.4 meters per second squared, and so that's going to be equal to mass 50 kilograms times acceleration 0.4 meters per second squared. All right, and so just writing the equations, this is probably just saying t minus F of gravity is equal to may is sufficient to write the equations plus this one. But for solving down here, we're using this information up here. And so let's just rewrite this down here because it says find the tension now. So we've got t minus 490.5 equals 50 times 0.4. 50 times 0.4 is 20, yes. All right, so t, bring the 490 to the other side. 490.5 plus 20. 510.5. All right, and let's see. We only have one significant digit there, so this force number really should only have one significant digit. So anyway, we'll say tension is 500 newtons. All right. On to number 9. We've got stuff down here. Try to get it so we can see. Football player kicks the ball off the ground, starting with a velocity of 15 and an angle of 40 degrees. So we got something going like this. V naught is 15 meters per second, and then the angle is 40 degrees. All right, so we've got x and y components of velocity. Vx0, Vy0. oh, sketch situation, limit, labeling vy0, vx0. So then this point here is going to be x0, y0, the starting point. And I guess I just did it right there. Didn't need the space, or put it up there instead of down here. Okay, we can calculate vx0. It's not really needed here. Well, down here. Find the vertical and horizontal components of the velocity. So that's asking what is vx0 and what is vy0. Okay, I've got weird space issues here, but vx0 is the sideways component. We got v0 as a hypotenuse of the triangle. And so vx0 is going to be v0 cosine, because it's next, vx0 is next to the angle of 40 degrees. v0 was 15, so it's 15 cosine 40 degrees. So 15 times cosine 40, 11.5 is Vx. Let's see, let's put some units on there. Well, let's see how many sig digs we need. 11.5 meters per second is Vx0, but we wanted just 2, so that'll be just 12 meters per second for Vx0. Similarly, Vy0 is Vo, but the y is the opposite angle, so it's sine. Vy0 is opposite the angle, and so that's 15 sine 40 degrees. And that's going to be 9.64 meters per second, Vy0, but 2 sig figs gives us 9.6 meters per second. Okay. That's it for B. Part C. How long does it take the ball to reach its peak height? Peak height. So what do we know about the peak height? So that we're going, it's supposed to be a parabola. We're asking about this point up here. We have the V0, 40 degrees stuff here. And so we know at the peak, in terms of height, in terms of velocity in the y direction, it gets to be 0, right? It's going up, up, up. Now it starts going down. So in the middle, it hits a 0 point. So we know that Vy0 is down here, but Vy at the peak is equal to 0. X still has a component. The x component, Vx, is just still going to be Vx0, right? Remember with projectiles, once they're in the air, the sideways velocity stays the same all the time. And so Vx0 is still the same. Vx is the same as Vx0, which we calculated was 11 point, we'll use the more sig digs, 11.5 meters per second. Okay. All right. So how long does it take to reach its peak height? So we need an equation that has height in it. We need an equation that has time in it, right? Because we're asking for what is t when it reaches peak in y, right? We've got x and y. So remember when we have projectile motion, we have 2 sets of position equations. And so we can write y equals y0 plus vy0 t plus 1/2 ay t squared. Right, just our position equation, but in y. We've got y0 is equal to 0. We got y. Do we know y? We don't know y. Okay. Let's keep going. We vy0, we've got that. We don't know t. We know ay is negative g. All right, we don't know enough though because we got y and t are 2 unknowns. Okay, let's look at a different equation. We have our velocity equation in the y direction. Vy is Vy naught plus AT. All right, fewer numbers, maybe we know them. Again, we know A is negative G. We know Vy naught from the other page. Vy naught is 9.64. All right, and Vy, we just said at the peak Vy is equal to 0. All right, so I like this equation better, right? So we can rewrite it. We're going to say 0 is equal to 9.64 plus, well, negative 9.81 times t, right, for g. Solving this for t, we're going to get t is equal to 9.64 divided by 9.81. You can do a few more steps of algebra. Bring this to the other side, divide through by 9.81. 9.64 divided by 9.81 is 0.9827 seconds. Again, only 2 sig figs, so t is equal to 0.98 seconds. T to the peak. How high does it go? Well, now we can use this equation up here. So y equals, we said y naught was 0 plus v naught, Vy naught is 9.64 times t, we got t now, 0.9827, plus 1/2 a, negative 9.81, times t squared, 0.9827 squared. I'll plug all this in. Always better to put parentheses around things when you put negative numbers in a multiplication here, just to be safe. Alright, and we end up with y is equal to 4.74 meters. Again, 2 sig figs, y equals 4.7 meters. See how that looks compared to my previous answers. Looks good. Okay. Now it says, how long does it take for the ball to hit the ground? All right, so now we're not talking about this situation up at the peak. Now we're going to change to looking at a point down here. So we're going all the way over here for y. Y is going to be back to being 0. X is a new distance, the whole length of the kick. We still got our same v naught, vx naught, vy naught stuff, but our x and y kind of information is changing. What can we, well, like I said, we can say y is equal to 0. So how long does it take to hit the ground? I think we can use our y equation for this. So I guess I'll rewrite it. Y equals y naught plus vy naught t plus 1/2 at squared. In this case, a still negative g, vy naught still what we had before, 9.64. Negative g, that's what that says. Okay. Y naught is starting at ground level, so y naught is 0, and then y itself is also 0 because it's hitting the ground over here. All right, and so we can just plug in. So 0 equals 9.64 t, because t is what we're looking for, plus 1/2 negative 9.81 t squared. And we can factor, so we got 0 equals t times 9.64 plus, well, if we multiply half times 9.81, we get times negative 9.81, we get 4.905. times t, and then close parentheses there. And so, again, the way algebra worked with factoring, if this something times something equals 0, either the first something or the second something has to be equal to 0. So we get one solution that says t equals 0, which is talking about this point, which we already knew. We don't really care about that one. But now we're going to set this part equal to 0. So 0 is also equal to 9.64 minus 4.905t. So that says that, let's go up here a little bit, t must be equal to, bring this to the other side, divide through by the 4.905, 9.64 divided by 4.905. 1.965. Okay, so 2 sig figs, 2.0 seconds. Okay. How long does it take to hit the ground? That's it. So some of you ask, well, what would we do, or will we have a problem where it doesn't end up where it's at 0, right? The two y's are not the same. And so that makes it a little bit more complicated, right? Because we're going to have, say it started at 0, but somebody caught it up here or something, or it hit the goalpost or something. And if we had the ending y was, say, I don't know, 1 meter off the ground, right? What does that do to this problem? Well, looking at this equation, that makes this ending y not be equal to 0, okay? If we had a problem where, like in lab where we rolled the ball and it fell down here, we might have had y0 not being 0, and then y was still 0. But whatever happens, we're going to have a constant part over here. So let's just take a side minute here and see what would happen, how we would do this part if the y's were not equal, or it wasn't starting at the ground and hitting the ground again. So say we did this case where it's landing 1 meter above the ground on something for some reason. Okay, so we would have 1 for y is equal to 1 now, equals y naught, we can still say that's 0, plus v naught t, vy naught t, 9.64 t, and then minus 1/2 gt squared, so minus 4.905 t squared. All right. And so now we've got a quadratic equation. It gets a little messier, right? So let's rearrange this and put it more in standard form. We have 0 equals something times t squared, negative 4.905 t squared, plus 9.464 t, and then bring the 1 over to this side is minus 1. All right, when we have our regular quadratic equation, right, it's in the form 0 equals at squared plus, usually we do lowercase, at squared plus bt plus c, right? And the quadratic equation says that t is going to be equal to negative b plus or minus square root b squared minus 4ac all over 2a. All right, so if this were the problem that we were doing, we would then plug in the numbers. So in this case, b is 9.64, negative 9.64, plus or minus square root of b squared, 9.64 squared, minus 4 times a, which is negative 4.905, running out of room, times c, which is negative 1. Right, all of this over 2 times a, 2 times negative 4.905. All right, simplify it. Let's just rewrite that because it got kind of a mess over there. Negative 9.64 plus or minus the square root of 9.64 squared. Well, let's just, okay, so we got minus 4ac. A and c are both negative, so we can just kind of cancel that out, and c is just 1, so it's going to be 9.64 squared minus 4 times 4.905. Right, and the negative 1 is gone with the negative sign all over. This is going to be negative 9.81. All right, plug those into your calculator. Negative 9.64. We'll do the plus first. Plus square root 9.64 squared minus 4 times 4.905. Get out of the square root, put that in parentheses, and divided by negative 9.81, which is 2a. I just multiplied that in my head and knew that came from gravity in the first place. Oops, what? Okay, what did I do? Maybe I made an impossible problem. Minus 4ac. Oops, I forgot to square my 9.64. I was getting imaginary numbers, which are not good for this problem since it's all real. There we go. All right, so for the plus, I get 0.1099 seconds. For the minus, let's go up there, grab that again. It's good to have a powerful calculator here. Go over here and change that to a minus, and I get 1.855 seconds. All right, so two answers. It's quadratic equation. You got t squared, so that means they're going to be two choices for t. Does it make sense in terms of the problem? Yes, because in the first time it goes to 1 meter high over here first, then it comes back to 1 meter high over here. So there are two places where y is equal to 1 meter high. So we don't want the first one because that's over here. We're assuming it went up and came down was where we're looking for. So then this would be the t that we're looking for. All right, so it is a bit messier when you have the situation where it's falling off the ground or falling off, anyway, where the initial and final heights are not the same. All right, it gets a little bit trickier when you're trying to solve for t anyway. Okay, so that side note, not really part of the question, but somebody asked about that in class, so I thought I'd explain how to do those kind of problems. So we're back to our problem here where we had initial and final height the same, and so we got t was 1.9605. Okay, so how far does the ball go? And so in this case, how far is asking about x. All right, x equation, same kind of basic format as we had before. X naught plus v x naught t, that's an x, plus 1/2 a x t squared. All right, what do we know? Well, vx naught was 0. I'm sorry, x naught is 0 itself. Vx naught we had from before. Vx naught was 11.5 meters per second. A sub x, for all these projectiles, once they're in the air, there's no acceleration. There's nothing keeping them from going, nothing slowing them down or speeding them up in the x direction. So a sub x is always 0 for these projectiles just under the influence of gravity. So a sub x is 0. So rewriting this, we're going to just have x equals 0 plus v sub x naught, 11.5 t plus 0. All right, so this is all we have here, and we just figured out t. So 11.5 times 1.965. So x equals 22.6 meters, or just with 2 sig digs, x equals 23 meters. All right. For this other one, it would be exact same. Once you've got t, just plug in this equation and calculate how far that would be. All right. Okay, I think that's the whole test. We'll stop there.